Alright, welcome back. Let's talk about time complexity and let's differentiate the names of the different time complexities. So, omega notation, the symbol omega, represents best case scenario, the lower bound, the smallest cost associated with time cost associated with doing something. The upper bound, the worst case scenario we're looking at, is the big O notation. And let's see here. Big O. And then average is the in-between, is theta. So we hope for the best, plan for the worst, and like fuel efficiency for cars, they don't tell you what's worst case scenario, they tell you, well, here's the average. In programming, I want to know the worst, let's plan for the worst. So in this example, I'm going to say I is initialized at 6. Let's go through this loop from 6 is less than n. I don't know how big n is. It could be really, 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 really big, like 25 trillion, or it could be 25. And the size of that number matters, how long it's going to take to get this processed. So it's the size of that number coupled together with the capacity of the processor for this device. So those two things are going to play into how long does it take to do the work. So with that said, we're going to go through this, and it ends up, we're going to be n minus 6 is how many iterations we go through it. So this is linear. There's a direct correlation between n and how many times we go through this loop. So we would call that big O of n. So n being a linear time. And we saw examples where it compares in the text and examples in the resources where it compares constant time, linear time, exponential time, or cube time, quadratic time. And we see how the different times, what's really good efficiency, what's really bad. So when we look at this and we say, well, it's linear, it's not great, but it could be a whole lot worse. We come down to this one, and this code's similar, except for this. So this one says I equals I plus 1, so we increase by 1 each time. This is different. So the growth rate I is raised by the power of 2 on each iteration. So it's I, which is 2, and then we say, alright, so it's starts out I to the 0 is 2, I to the 4, so that's 2 to the 4th power, so that's I1, the first iteration through. The second iteration through is I, which is 2, to the power of 2. Oh no, excuse me, I've got it at 4 here. So 2 to the 4th is the first iteration. Then it's 2 to the 4th to the 4th, which is 2 to the 16th. And then we say 2 to the 64th on the next one, and it's just growing by 4 each time. So the fact that we're growing by 4, man, I is getting really, really big, that value that we're dealing with. So we're not going through a lot of iterations because I is getting huge as we progress through. Compared to this, where I only grows by 1. So yeah, it's related to n, but we're growing through it really fast. So on this one, it's not linear because we're not progressing 1 by 1 by 1. We're progressing at an exponential rate. which ends up being log of n. All right. Let's look at this one. For I in range start at 2, go to n. Okay? So we know how many times we're going to go through this is directly related to n. All right. So this helps us. We know this part of the code, we're going to go through n minus 2. So it's directly related to n. So from there, for each value of I, j is initialized to I. So as we go through this, boom, boom, boom. So we're starting at 2 and going to n. So if it's 2 to 25, I is 2, I is 3, I is 4. This automatically increments by 1 and gets us through. So as we're doing this, we're increasing j by 1 every time we go through this loop. Then we've got this inner loop. While j is less than I. Well, we're going through that while j is less than n, excuse me. We're going to go through this until we reach the end of our array, if you will. So this one we're going to go through n minus 2. This one is not going to be n minus 2. This one increases, so it's like j equals j times 4. So first go, j is I. And then we've got 4 times I, 16 times I, 64 times I, 256 times I. J grows exponentially as we go through each iteration. So kind of similar to what we saw above. All right. So on this one, we'll look at this and we say, well, for this loop, the time complexity is linear, so it's big O to the n. This loop is big O to the log of n for each I. So the total time complexity is big O n log n. So let's go see what we have left. We'll start out, we'll initialize I at n. Let's say that should be a little I. While I is greater than or equal to 25. Let's print adversity. And then we're going to say I equals I divided by 2. So we're decreasing the value of I as we go through it. Okay, so we start out I is however long n is, so that could be 25 trillion. I is greater than or equal to 25, cut it in half, cut it in half, cut it in half. So when we think about this cutting in half part, and we'll talk about it later, what will come into play is the divide and conquer algorithm. So on this one, since we're dividing by 2, we're directly related to n, and it's essentially n divided by 2 times 2 times 2 times 2. So it's like saying n and then n divided by 2, n divided by 4, n divided by 8, n divided by 16, and that grows. So what that boils down to is O to the log of n. this is like our divide and conquer logic. Okay, now let's go ahead and we'll look at another one. So here we have one I initialized at 6. While I is less than n, and we're going to increase I. We're going to say I equals I times 5. All right, so we're moving through pretty fast. So this is very similar to the others that we've done. We know that we're going through less than n. Started at 6, we're going to get through this. We increase by 5, so we're not going through a totality of n, it's a factor of less than n. So with this one, we're looking at big O of log of n. Okay, it's a last little code snippet that I've got. But when we look at, let me do another one. Let's say that, I'll copy this and we'll rework it a little bit here. So let's look at these code snippets. So look at this one here first. So for I in range 0 to n, we know that we're going to go through this n number of times. And we've got another loop in here that's going to go through n times. So I've got n here times n here equals n squared. What we had up above was n times log of n, or we'll have log of n, depending on how it's set up. And now we've got another example here. Let me bring it down to where it's all in the same place. N times n times n. So this is cubic, n to the third. How bad is this number? Well, time complexity wise, this is a really bad scenario because this is going to take a lot of time. So this is the equivalent of, an example that I've given, let's say n is 25, that would be 25 to the third power. Or 25 trillion to the third power. That's how many tasks or operations are being performed. And when we look at evaluating our code that way, that's a lot of time. But when I say a lot of time, I mean a huge difference in time between 25 cubed and 25 trillion cubed. The value of those two numbers is vastly different. And if we looked at it as, well, it'll take me 25 days to complete my work. Well, it's 25 times 25. Well, that's a big number. All right, we'll bring it down. How about 25 minutes? 25 minutes cubed, it's still a big number time-wise. How about 25 trillion minutes? You're not going to be alive when it's done. So we need to be able to look at the code and say, yeah, time complexity on this code, this little code snippet, is really ugly. It's going to take a long time to do it if n is really big. So we've got to plan for the worst case scenario And the worst case scenario is two things. One, our big O notation, worst case scenario when we're talking time complexity. And we need to plan for n being this enormous number, massive amount of data coming in. We want our code to be functional, but we also want it to be scalable. Okay? And there's trade-offs. We'll talk about those in future modules.